In this session, I shall talk about cross products. A cross product is defined in this way. Suppose we have two vectors, a vector A and a vector B. Right, think of this as a three-dimensional drawing. It's a bit difficult since this is just a piece of paper, but imagine that A is slightly in front of the paper and B is slightly behind the paper. Then the cross product is written in this way. It's written as the vector A with a cross which looks just like a times. Right? That would be A cross B. That's the symbol used. Now this cross product is defined as a vector. Right? So this is a vector. Right, next we are going to describe this vector. It's a vector. The length of this vector, I shall describe it using this symbol, the two lines here, for the magnitude of the vector. The length of this vector is equal to the length of A times the length of B times sine of the angle between them, sine theta. And we also need to describe the direction. Alright, and this vector is perpendicular to both A and B. Both A and B. So if A and B are on the paper, we could think that this vector A cross B is perpendicular to the paper, like this pen here. But if I'm trying to draw a 3D picture, and I think that the vector A is pointing out of the paper and B pointing into the paper, then I could draw a vector on the paper like that and try to imagine that this is a three-dimensional drawing, so that this line, this vector is at the same time at 90 degrees to B and also at 90 degrees to A. And that's A cross B. But this description that is perpendicular to both A and B is not enough to specify the cross product, because a vector perpendicular to both A and B could also point in the opposite direction. In order to specify which direction, we use what is called a right-hand thumb rule. It means we use our right hand and we imagine fixing this point, this tail end of both A and B, and then imagine that A is like a piece of rod, and we think about rotating vector A towards B. Right? Think about rotating A towards B. Then you hold out your right hand and you curl the four fingers. All right, you curl it around in the direction that A rotates towards B, and then you stick out your thumb in the perpendicular direction. Then the thumb points in the correct direction for A cross B. So to describe that, we might say that it's perpendicular to both A and B, and it is in the direction given by the right hand thumb rule. Okay, when the vector A rotates to B. All right. Of course, A does not actually rotate to B. This is what we would imagine in order to determine the direction of this vector. That is across the definition of the cross products. Now, what I want to do in this session is to prove two properties of the cross product. Right, hopefully there'll be time to prove both properties. If not, I'll prove the first one first. Now, the first property that I want to prove is that suppose that the vector A has components AX, AY, AZ, that the vector B has components BX, BY, BZ. Then this first property is a formula to calculate the components of the cross product. And this formula, A cross B, is sometimes written in this form. I, J, K, and then AX, AY, AZ, and then BX, BY, BZ. What this means is this. I is a unit vector in the x direction. Right? J is a unit vector in the y direction, and K is a unit vector in the z direction. So these are the meanings of the IJK. And if you have not seen this symbol, these two long vertical lines before, that's alright. I'm just going to write out what this means right now. This means that I would calculate the components of the cross product by writing out first the vector I and then multiplying it by, okay, I'm going to get ready a bracket. I'll multiply it by AY times BZ minus AZ times BY. Now this formula is called the determinant of, if I look at this 2 by 2 arrangement of numbers, which is usually called a matrix. So this two vertical lines is really means determinant of the matrix. And what I'm going to describe is the procedure for writing out the formula of a determinant. Okay, so the next term, the first term is obtained. The usual way to think about how to obtain the first term is to say, if you start from I, then we imagine crossing out the vertical column and row, so that only this smaller matrix remains. Then when we take the determinant of a 2 by 2 matrix, we would multiply across like that to get the first term, and then we would multiply across the other way to get the second term, and then we subtract them. That's how we calculate the determinant of a 2 by 2 matrix. The next term we would go to J, and then imagine crossing out the row and the column that contain J. Then we are left with these two elements and those two elements. So together, those two and those two form a 2 by 2 matrix. And we would calculate the determinant of that in the same way as before. I would multiply across AX, BZ, and then I would go across the other way, AZ, BX, and then I would subtract them. Okay, and in this formula, I'll come back to that in a moment. Let me now go on to the third term. The third term, we would then go to the K, and like for the J and I would cross out the column and the row that contain K. Then I'm left with this 2 by 2 matrix. Then I would find the determinant in the same way. AX BY minus AY BX. AY BX. So that's that. Finally, I have to put in the signs. For the first term, I have 3 terms here. For the first term, the sign is positive. The second term, the sign is negative. And the third term, the sign is positive. And that's a very complicated thing to do. And hopefully you'll become more familiar if you learn about determinant at some point. If not, then, if you know determinant, then this is a quick way to remember the formula. If not, then you would have to remember the formula using this longer expression. So either way, that's fine. And it is this that I'm going to make use of, that I want to prove. Right? The first property that I want to prove is that the cross product is equal to this. Alright, I'm not trying to prove that the determinant is equal to this. Alright, that's just the definition. Writing this out from here is just how determinant is defined. So what I want to prove is that if the cross product is a vector that is described by these features that I have sketched out, then the components of the cross product must be given by this, and this. Okay, That's the other thing we should note about the meaning of this formula, which is that the number that is multiplied by I is just the x components of this vector, since I is a unit vector in the x direction. And for y, that's the y component with the minus sign, and that's the z component. So if I'm to write out the vector components in this way, for example, bracket with commas in between, I could also write it out like that. It's equivalent to writing. I'm just going to copy it out. The first term is that ay bz minus az by. The second term is that with the minus sign. So if I remove the bracket, it would be just minus ax bz plus az bx from there with the minus sign. And the z component would be just that, ax by minus ay bx. So that's yet another way of writing this, writing down the components. But this is the first property that I like to prove. The second property that I want to prove is that if I have, this time if I have three vectors, vector A, vector B, and vector C. Suppose I have the three vectors. Then we want to prove that if I take B, if I add B to C to form a new vector, and then I take the cross product of A with this new vector, the answer is the same as if I first take the cross product of A and B, and then I take the cross product of A and C, and then I add them together. Now this expression looks very familiar. Now if you have seen my earlier session on the distributive property of dot product, you will know that I've explained that in the case of dot product, we should not think that an expression like this is obvious simply because we have seen it before for simple numbers, right? If A, B, C are just simple numbers like 1, 2, and 3, then this is just what we would get when we remove the brackets for simple numbers. But in the case of the cross product, we are not doing a simple multiplication of two numbers like 1 times 2. The cross product, although the cross here looks like a times, it's actually not the same meaning as the times that we use for ordinary numbers. Right? It's actually something quite complicated. This cross down here, which looks like a times, all right, this cross in between the two vectors, it actually tells us that the answer is another vector that is described by this long description which I described just now. So hopefully that would convince you that this is not just a simple multiplication. And that also means that because this is not our normal multiplication, this relation, all right, is not obvious. It's not like removing the brackets. So that means that if we want to say that this is equal to this, we really need to prove it properly. But this property, it does have the same name that is used for the simpler case if A and B are just numbers, because A, after doing this operation, it clearly becomes distributed to both B and C. That means it is as if each of B and C gets its share of the vector A. Because of this feature, this property is called the distributive law. In this case, the distributive law of cross products. And this is what I would like to prove. Okay. Right, it looks like it has taken me quite a while just to explain what I want to prove. And now let me make a start on the first property. Now I shall briefly describe the plan for proving the first property, because that proof would be quite involved. And the plan is this. Now recall the definition of the cross product. It is defined as a vector that has this magnitude, and its direction is defined to be perpendicular to both of the vectors. Now the plan for proving this formula, or if that's more familiar, this formula is to first do it for a vector that is in the, let's see, right, I'll look at that. That is in the xy plane, meaning not just any three-dimensional vector pointing in any 3D direction, but let's start with the simpler case where both the vectors A and B lie in the xy plane. Right, so I would start by proving that simpler case, and that means that as I'll explain, I would only need to look at this one component in the results. Then I shall extend this result to the more general three-dimensional case. Okay, that's the plan. Property 1. So we consider both A and B in the xy plane. Okay, so let me try and draw this. All right, first I'll try to draw a 3D picture to show what I'm trying to do. So that's these are the x, y, and z axes, and suppose that A is this vector and Okay, and B is that vector. Both lie in the xy plane. Let's just have a look at this and think about what the cross product might look like. The cross product, as I have described it just now, is a vector that has right, A cross B, that has a magnitude of AB times sine theta. Theta here is the angle. And it points in a direction perpendicular to both vector and following this right hand thumb rule. We can see that since A and B both lie in the xy plane, it is the z-axis that is perpendicular to both of these vectors. And as I've drawn it, if you imagine rotating A to B, then our right hand thumb rule would tell us that if you rotate from A to B, the direction should be upwards, which is what I hope to show with the z direction here. So that means that the A cross B direction should be along the z-axis. Okay, so that's how we can understand the cross products when both A and B are in the xy plane. So we have a good understanding of the direction now. A cross B is in the z direction. We know the direction, we know this formula. The next thing I want to do in this proof is to show that is to think about the physical meaning of this AB sine theta. The physical meaning is quite simple. If I look at, say, I'm now going to just focus on the xy plane. So I'm going to look straight down. That's it. Like that. Okay, so the z direction will be pointing upwards. And that's vector A, that's vector B. Now the meaning of AB sine theta is simply the area of this parallelogram that has A and B as two sides. And to understand why, think about B sine theta. That angle is theta. B sine theta is the length if I drop a perpendicular from B to the vector A. Because then this forms a right angled triangle and the length of this hypotenuse is B, that's the angle, so therefore the opposite is B sine theta. Right, that's my B sine theta. And since this is a parallelogram, those two sides are parallel. If I think about the side A, I'll rotate this a little bit. Okay, so if I imagine that that's the base of the parallelogram, then this is the height. And we know that area of a parallelogram, that's how we might write parallelogram shorthand, is equal to base times height. And in this case, the base is A and the height is B sine theta. And if you look back at the magnitude of the cross product, we we see that this is exactly the magnitude of the cross product. Okay, so this is magnitude of A cross B. So in this simple way, we now have a physical meaning or geometrical meaning for the cross product. It's the area of the parallelogram formed by vector A and vector B. Now this geometrical understanding would be helpful in what we want to do next. So the next thing that I want to do, if we look back at what we want to prove for some guidance, let's see. Now remember, from what I've described so far, we know that if vectors A and B are both in the xy plane, then the cross product points in the z direction. If I look at this formula that I want to prove, the formula for the components of the cross product, we should look at the z components. Alright, it just means that if A and B are both in the xy plane, since the cross product points in the z direction, therefore this component should give the magnitude of the cross product, and those first two components should be 0, since this vector should be perpendicular to the xy plane. And it's quite easy to see why those two components should be 0, because if you look at each of these components, they all have a z component for B and z component for A. See, z component for B, z component for A. Now all those must be 0, because A and B lies in the xy plane. So in order to prove this, therefore, let me write down what we need to prove in this special case. So we need to prove that A cross B is equal to a vector where x component is 0, y component is 0, and z component is given by the formula so that's what we need to prove. And we already understand why those two components should be 0. In a sense, we have already proved that these two are 0 simply by saying that because A and B are both in the xy plane, therefore both of them do not have components let's see. No, that was how we obtained the zeros, right? Because these are 0 from the formula. Okay, let's try to be clear about this. These are 0 these are 0 from the formula because A and B do not have components in the z direction. and we have all the AZ and BZ in the first two terms. So because of this, when we substitute into the formula, those two should be 0. Right. So these are 0. Because AZ, BZ are both 0. Okay. But that's not what we need to prove. We need to prove that according to the definition of the cross products, those two are 0 and this is true. And according to the definition, we know that A cross B must be in the Z direction. Okay, so and it is this result which proves that those two are 0. Okay, so let's clarify this. So first I know that those two are, I wrote down these two are 0, that this is what we need to prove. Okay, because this is the formula that we are supposed to prove. This is what we need to prove. Now and then we prove these two are 0 by saying that and in the proof that the x and y components are 0. So that means that one and that one. Because A cross B is in the Z direction. By definition. So this proof is by using the definition of A cross B, whereas those two are 0 comes from the properties of A and B in the xy plane. Okay, so these are two different properties. Now moving on from that, we now need to prove the last component, that this is correct. Now since both of these are this and this are 0, the last component must be equal to, must give the magnitude of this vector. All right, it does not have to be equal to because it can be negative. All right, but the magnitude of this would also be the length of this vector. And in this case, as we've seen just now, we know that the magnitude of the vector is actually geometrically equal to the area of this parallelogram. So in order to prove this, we can look at this parallelogram and see if we can show that the area is actually equal to this formula. And this is what I'll do next. So in the next step, right, let me draw out this figure and see if we can relate the area to the components AX, AY and BX, BY. Okay, so that is B and this is A. Now the plan is this. I shall start by finding the area of this figure. Okay, that means the whole thing. And then I shall find the area of this figure in terms of AX, AY, BX, BY. And then I'll subtract the big area from the small area to find the area of the parallelogram and show that that gives the correct formula. So let's start. To find the area of this, so let me shade this just to avoid confusion. This is the area that I want to find. Okay. Now the thing about dividing this area up in this way. It's better to draw a separate picture here. It's the B. This is the A parallel to that. Okay. Now I'm going to divide this up in this way. In the triangle here and a triangle here. So the components of A is AX, AY, and that means that this length is AX and that length there is AY. Components of B is BX, BY, so this length is BX, that height is BY. Now you can see that we now have a very simple way to write down the area. This area is half base times height for this triangle. So half of BX, BY. That area is just a rectangle, it's AX times BY. And that area of the triangle is half base times height again, half AX, AY. That's simple enough for this big triangle. Now it's looking quite promising because we can obviously try and apply the same idea to find the other parts of the figure. So now I shall try and find this area of the figure. Okay, let me see, try and draw that part out on its own. It looks like that. That's the A. That's the B. That's the area we want to find. So I'm going to divide this up in a similar way. Okay, and the area here would be, right, the area of this triangle, this is AX, this is AY. For this is BX, this is BY. You can see that this is the same as that triangle. Therefore, the area of this triangle is half AX, AY. This rectangle is AY, BX. So this rectangle and that triangle is half base times height. Half base times height. And now I can find the area of the parallelogram by taking the difference of those two. Difference. And if you compare the two, you find that this is exactly the same as this, and that is exactly the same as this. So that's very nice because those would all cancel, and I'm left with just this minus this. AXBY minus AYBX. Now, you might notice that this looks familiar. Well, it is familiar because it is exactly what I wanted to prove. So therefore, I have just proved it using this geometrical method. So I have, therefore, if I come back to what I wrote at the start, I wanted to prove the first property for the special case, right? This is a special case when A and B are both in the xy plane. So I've proved it, right? Because I've written down for the formula for the case when A and B is in the xy plane. I know that the formula must look like this with zeros here and this formula in the z direction. Okay, and from here I know that in order to prove it, I need to prove that this value is equal in magnitude to the area of the parallelogram of this. And using this geometrical method, I found that indeed the area of the parallelogram is equal to the expression that I want to prove. Okay, so I've done it for the case when A and B are in the xy plane. Now just one point to note. I've talked about showing that the magnitude of this is equal to the area of the parallelogram, but since we're talking about a vector, it's not just about the magnitude, we also need to worry about the sign. Now in this case, if you look at this parallelogram, because I obtained this formula by taking the bigger area and subtracting the smaller area, we know that in this example, this result must be positive. And positive means that the cross product points in this case in a positive z direction. Okay, but what if the cross product points in the negative z direction? Well, that could happen if we swap the positions of A and B. So if B is here and A is there instead. So how does that, what does that mean for the proof? Well, if you look at this picture, you see that A and B are there. If we swap the positions of the A and B, then basically that bigger area becomes the smaller area and the smaller area becomes the bigger area. So that when we subtract the two, I would end up with a negative answer because I would be taking a smaller area and subtracting a bigger area. So I'll end up with a negative answer, and this shows that it is still correct. Alright, this shows that I would get a negative value for the difference, and that gives me the correct direction if the cross product points in the negative z direction. Now so that completes the proof for the case when A and B are in the xy plane. Now we can see that the same proof can be used for the cases when A and B are in, say, the yz plane, and when A and B are in the xz plane. Right? If we think about these three planes. So what this means is, try and write out what it means. If you look back at the formula that we want to prove, it is this one. So we have shown that if A and B are in the xy plane, then this component, then this is correct basically, but because those two are 0, we only need to prove it for this expression. Okay, so if A and B are in, say, the xz plane, then we can go through the same steps and prove this component. And if A and B are in the yz plane, once again we can go through the same steps and we would prove that this component is true. So let me quickly write down this result. So if A and B are in the xy plane, we have just proven that A cross B is equal to 0 component in x, 0 in y, and ax by minus ay bx. So if A, so this comes from this formula there, and from what I've described, if A and B are in the say the xz plane, then A cross B would be, it would give that term, so 0 minus ax z, and that would be 0. And we should be able to prove this using the same steps similar steps as before. And likewise, if I have A and B in the yz plane, then A cross B would give the first term there, and zeros here and here. Alright, so we can write down these results without having to go through the proofs again, because the three planes are all symmetrical. So this is the first part of the proof for the first property. We now need to generalize this, extend this proof to the case where A and B do not lie in any of these planes. What happens if it just points in any direction in 3 dimensions? Okay, let me try and draw that. It's always difficult to draw something in 3D. So suppose that I have A it might help. It might if I use a pen with a different color. Say suppose that is A, suppose that is B. Okay. Now, in this case, in this very general case, the cross product, as described before, must be perpendicular to both A and B. Now let me try and draw that as well. Let's say it is somewhere here in this direction. Okay, perpendicular to both A and B, A cross B. So what can we do to demonstrate that the formula is also true in this general case? The way to do that is to think about right, we have the vector here, is to also think about the corresponding area that is formed by the sides A and B. Now, in the first part of this proof, I have described how when A and B are in the xy plane, how the parallelogram area is actually equal to the magnitude of the cross product. Now the same is true in the 3D case, right? With A and B pointing in any direction, not necessarily in the xy plane. It is still true from the definition that A, if we think of A and B as forming the sides of a parallelogram, right? If you think about this parallelogram, then this angle is theta. Then the area is still given by AB sine theta, because that's the general formula for a parallelogram with sides A and B and angle theta in between. So this geometrical property is still true. Right. Now the way to prove it for this general case is to consider the projections of the area into each of the three planes, each of the xy plane, yz plane, and the zx plane. Alright, and for each projection to the xy plane, prove that the area, alright, that is projected onto the xy plane is equal to the vector A cross B projected along the z direction. Let me write that down. So in this part of the proof, right, so this is the next part of this proof. I need to prove that the area of the parallelogram this parallelogram is equal to the area of the parallelogram projected on the xy plane. Alright, projected means if you imagine there is the sun shining from the top, the sunlight coming from the top, it forms a shadow on the xy plane. Okay, so that's the projection that we're talking about. The area of the shadow is what we're interested in. So the area of the parallelogram projected on the xy plane, or if you like, the area of the shadow on the xy plane, like shadow, is equal to the components of the cross product A cross B in the Z direction. Right, we want to prove this. Maybe that's the first part, and then we want to say that we want to repeat this proof for the other two planes. So for YZ and ZX planes. Now before we actually launch into this proof, let's think a little bit about why this works. Why is this what we need to do? Or even why this is true from the definitions. So what we had just now, if you look back at the proof itself, the property itself that we want to prove, is that we have this formula, Alright, we want to prove that the cross product is given by this formula. And in the first part of the proof, we have shown that each of this component is actually equal to the area of the parallelogram if those two vectors are in that plane. So if the two A and B are in the xy plane, then this component, this z component, is equal to the area of the parallelogram formed by A and B. So that's what the first part of the proof has shown. And now if I want to actually show it for the general case when A and B are in any direction, basically what I need to show is that first, according to the formula, this is in this appears to be connected to both the z component and the area and an area in the xy plane. Okay, so because of this, if I can show that this expression is both equal, that if I can show that in the case where A and B is in the general 3D direction, if I can show that this component is still equal to, is actually equal to an area projected into the xy plane, then let's see, I need to make use of the property from the definition that A cross B is perpendicular to the area. Now if I can show that the projection of this area onto the xy plane is given by this formula, and if I can show that the components of the cross product as described by the definition, alright, if I can show that the component of the cross product in the z direction is also equal to the same area, then that would show that this expression here gives the correct value for the z component. So let's try and do that. So for the step 1, what I need to do is to show that the area of the parallelogram projected onto the xy plane is actually given by the same formula that gives the z component here. And to do that, we can start by thinking about the coordinates, the xy coordinates of the corners of the parallelogram when it is projected down onto the xy plane. Now, since the components of the A and B are given by this, when it is projected onto the xy plane, it means that we simply have to just consider AX, AY and BX, BY, because the projection on the xy plane has no z component, so those two become 0. So all we need is to ignore those two. Okay, so that means that the projection of A, B in the xy plane, right, are just AX, AY 0 and BX, BY 0 are given by this. And if we just look at the xy plane itself, we just need to look at those two. But we already know what the area of the parallelogram formed by those two vectors are. It is simply from the first part of the proof just now. Okay, when those two are just the projection onto the xy plane, and we have already proven that it is the area of the parallelogram, which is given by this expression. So from the first part, alright, we already know that this projected area is equal to AX BY minus AY BZ. So we already know this. So that's the projected area. So the next thing I need to do is to show that the component of this in the z direction is also equal to this. Now, of course, I cannot make use of this formula that I want to prove and say that, right, that's the z component of the cross product, so therefore it is equal to the area, right? Thing is, I cannot make use of this because this is what I want to prove. I have not proven it yet. So that means that to show that the components of this in this direction is equal to this, I need to think of another way of doing it. Okay, so this is the projected area in the xy plane. I need to do that using the definition. Now let's recall what the definition tells us. Definition tells us that the length of this vector is equal to AB sine theta. Alright, it just means that the length of this vector is equal to the area of this parallelogram. So, how can we connect the component of this in the z direction to the projected area? So the idea is therefore to do it completely geometrically at this stage. So if I want to do it geometrically, well, let me think about, say, this angle. To find the component in the z direction, I can find it in terms of this angle. Okay, let me call this angle, say, alpha. Right? So if I think about this right angle triangle, this component would be the length here, which is the area of the parallelogram, times cosine alpha. So just to make it easier to write, instead of calling it AB sine theta all the time for the area, I'm just going to call it capital A. So that's the next thing that I want to do, right? The component of A cross B. So the component of A cross B in Z equals area of the parallelogram formed by AB times sine alpha. Right, so that's that, sine alpha. Now, the next thing that we need to do then is to think about finding the area projected onto the xy plane. Think about finding that geometrically as well. If I project this area, I can imagine projecting each corner. So let's say that corner. Let me use this pen. This corner, that corner, so that I have an area that looks like this. Now you can see that because because A cross B is tilted to the vertical at an angle alpha, and because this A cross B is perpendicular to both A and B, right? Therefore, this area of this area enclosed by A and B, this whole area, the plane of this area is tilted with respect to x and y by the same angle alpha. Right? To understand that better, think about the xy plane. Right? Z is perpendicular to the xy plane. Now imagine that we start tilting the whole of the xy plane, and that z will tilt with it because z has to remain perpendicular to the xy plane. Imagine that we start tilting the xy plane, okay, like that, and the z here. As you tilt the xy plane, the z tilts. And if you tilt the xy plane so that it moves into the plane of this parallelogram, then the z-axis will tilt until it becomes aligned with A cross B. So clearly then the xy plane must have tilted by the same angle as the z-axis, and which is that would be alpha. Okay, so from this picture, this visualization, you see that the A, okay, is at the same angle alpha to the xy plane. Alright. And because this parallelogram is at the angle alpha to the xy plane, it means that the area projected on to the xy plane must be equal to A times cosine alpha. So therefore, we have projected area of A on the xy plane is equal to A sine alpha. And now we have the connection. See, both of those are A sine alpha. In other words, the projected area of A on the xy plane is equal to the component of A cross B in the z direction. Alright. So finally, because we have shown earlier that the projected area, in the first half of this proof, we have shown that the projected area is given by the formula ax by equals to ay bz. So combining this, right, that's the projected area here and the projected area there. Combining these two results and these two results, we can finally say that this component of A cross B in the z direction is equal to this. We can finally bring those two together. Alright? So therefore, component of A cross B in z, right, is equal to this. Okay, so let me just summarize what I've done. This two part, this part, and this part, all right, comes from the definition. So this is from definition. This is also from definition. Okay, and this part here comes from what we want to prove, right? This is what we want to prove. This is well, that might be a bit misleading. We have actually proven this from the first part. Okay, so it is not that we want to prove the projected area, but it is this expression here that we want to prove. Right, this is the expression that we want to prove. Okay. Alright, so we starting from the definition and then making use of the first part, right? We have therefore proven that the component of A cross B in the Z direction is equal to this expression that we want to prove. Okay, so what I've done here is that I have proven that the Z components of this first property of this formula for the cross product, I've proven that this Z component is true for any vector A and B in 3D. So therefore, all I need is to repeat the similar steps and I would be able to do it for both the X and the Y component. Okay, and so this completes the proof for this first property. So we have taken nearly an hour and a half now. So let me finish this session now and I shall prove the distributive law in a separate session.